we have some few examples here to see. We're going to see some few, then you look at the other ones. That considered, we have this protection of a current relay protection system in the radial system network. And the faulty current here, if there's a maximum three-phase fault of 4800 ampere and the time multiplier setting is 2, find the operating time if the relay is a CO7 type. Okay, so here's the schematic that has been given, and also what has been given here is the logarithmic scale of a CO7, but we know that here is for time multiplier setting of 1 for the logarithmic scale here that has been given. Okay, but your question has specified the TMS which of 2, but the curve has been given for TMS of 1, the logarithmic scale has been given for TMS of 1. So we are going to see how we can employ the logarithmic scale of TMS 1 to obtain that of the TMS 2. Okay, so first of all, you need to know the current that is flowing in the line. To know the current that is flowing in the line, you simply use the formula of power divided by voltage. Since we know it's in three phase, we have the power, which is the apparent power, divided by root 3 times the line to line voltage, right? You know, in three phase, this is a formula. We're using root 3 because here's a line to line voltage. If the voltage was line to neutral voltage, we'll use 3, not root 3. Okay, so I believe you already know those differences. So when you punch, you have been given the power, right, which was 6 mega var. Yeah, uh, here is it, the power of that bus. You know, the power of the bus is still the same power which the generator produces. In powers, energy can neither be created nor destroyed. So the power on the line is constant. No matter if you're using a step up transformer or step down transformer, if you're stepping up voltage or stepping down the voltage, you know, when voltage steps up, current decreases. When voltage steps down, current increases. But when you multiply the two, it will still give you the same power. So the power at that bus is still the power in the whole system. Okay, so we utilize that to calculate the current. The current here gives us 230 ampere. So that is the normal current that is flowing in the line, right? Normal current, not a faulty current. That's the normal current that is flowing in the line. Okay, so the relay current, you need to know now what is the relay current. This relay current here is simply the current that flows to the relay at normal condition, right? So we have the relay, this normal current flowing the line. We know the normal current is the primary current. Then the relay current here is the secondary current. So utilize the primary current divided by secondary current, which is equal to the secondary winding divided by primary winding, which has been given. Number of turns, okay, because it has been specified 300 on slash 5. So 300 there is uh, 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 the secondary, then divided by primary 300. 300 is primary, 5 secondary. Okay, so utilize that relationship and you have to look for the I relay, which is I relay at normal condition gives 3.85 ampere. So with respect to this, that's what you use now to select the relay characteristic, right? So we'll select a relay of current tap setting of 4 ampere. So if you are going to go and buy a relay, right, for your protection scheme, you're going to buy the relay of current tap setting of 4. Why do we say 4? Because here, these are the various current tap settings for that CO7 that has been given. Here, you see 2, 4, 5, 6, 7, 8, 10, 12. So 3.85 is approximately near, is closer to 4. So we select that current tap setting of 4. So this is the characteristic of your relay which you want to use in the protection scheme. Now we have the faulty current. The faulty current normally was given as 4800 ampere here. Okay, so we need to set the relay based on that, on the faulty current. So If you have a current of 4,800, please, there's a mistake here, not 4,000, 4,800. Okay, but here it is, Apple, it is correct down here. So, faulty current here, you know that the faulty current at the level of the secondary, you know this 4,800 is a faulty current on the line, which is the primary. So, to know the faulty current at the level of secondary of the current transformer, that is what the faulty current that will be fed to the relay. So you still utilize the same formula up here. You take the faulty current times that ratio 5 on 300, which will give you 80 ampere. So this 80 ampere is a faulty current fed by the current transformer to the relay. But we are using a relay of 4 ampere. So if we are using a relay of 4 ampere, what we need to set in the relay is the current tap setting or the block setting multiplier. So that is a multiple of the faulty current. And how do we get that? We take this 80 ampere, which is the fault current fed to the relay, divided by the normal current of our relay, the normal characteristic current of our relay, which is 4 ampere. So 80 divided by 4 gives us 20 unit. You know, it doesn't have a unit here, right? Because ampere divided by ampere equals, it is a multiple. That's why we say a block setting multiplier. It is a multiple. So we are setting 20, not 20 ampere, right? So the block setting is a multiple. So 20. Because if you take that 20 times the 40 times the 4 ampere characteristic of the relay, it gives you what? 80 ampere, which is a faulty current, right? Okay, so we're setting the plug setting. Now, since we have the plug setting, you know there are two things we have to set here, the plug setting and the time setting. But now the time setting was given to us and it was required for us to calculate the operating time which the relay would react. So since we have 20 here, we look at the scale that was given for the plug multiplier setting of 20, what is the operating time? For the plug setting multiplier of 20, here we have 20 here. Here is 20. So you deduce the operating time here, which is 2.2 seconds. So that is the operating time, 2.2 seconds. But note that this is for a time multiplier setting of 1. Okay. But the equation specified that for time multiplier setting of what? Of 2 here. So since we know the plug multiplier setting is giving us 2 point, the plug multiplier setting of 20 gives us operating time of 2.2. So that's operating time for TMS of 1. So if TMS of 1 gives us 2.2 seconds, then for the TMS of 2, it will give us what? 2 times 2.2 divided by 1. That's simple logic. So gives us 4.4 seconds. So we have calculated the operating time which the relay will react. So that's it for that question. Example 2, similar. Determine the operating time of the infinite uh, 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 inverse time uh, characteristic relay of 5 ampere, 2.2 seconds, and having a clock setting of 125% and time multiplier setting of 0.6 connected in a network with a current transformation ratio of 400 uh, is to 5 with a fault current of 4,000 ampere. Here is the radial line that has been illustrated. Then same thing, TMS of 1 has been given the logarithmic scale, right? So we proceed with the same proceed similarly. So the faulty current is 4,000 ampere. Then if we have fault current as 4,000 ampere, then the current that will be fed to the relay during that fault will be what? That 4,000 times 5 on 400, which is the ratio, right? The transformation ratio there, which gives us 50 ampere. But now the relay was specified as a 5 ampere relay. So, and we have been given a plug setting of 125%. That is considered a plug setting of 125%. 125% is of that 5 ampere relay is 1.25 times 5. or 125 divided by 100 times 5, which will give us 6.2 ampere. So this is the actual relay characteristic, 6.25 ampere. So we'll now take that 40 current divided by this actual relay characteristic of 6.25 ampere. It will give us a clock setting multiplier. So that's what we use in setting the relay at 8, clock setting multiplier of 8. Then we can now deduce from the curve to find the time to find the time of operation. So at 8, we'll have we can extrapolate it to what? Around 3.3. At 8, we'll have about 3.3 seconds. So if on the TMS 1 is giving us 3.3 seconds, the equation was specified for TMS 0.6. So for TMS 0.6 will give us what? 0.6 times 3.3 divided by 1, which gives us 1.92 seconds. That's the operating time. Okay. Okay, then let's just you look at this other one. Look at this other example to understand it. But now this other example is quite a little bit different because here the coordination aspect has been considered. That okay, if the first circuit breaker is or the second circuit breaker is the one to react for a fault probably at the other end of maybe bus one, and probably you have circuit breaker 1 did not react, circuit breaker 2 has to react. Then you need to consider the time of circuit breaker 2 plus the coordination of circuit breaker 1 plus the coordination time. Okay, but now the other procedures to measure or to have the clock settings are the same. First of all, determine the current in the line, which is T what? The apparent power divided by root 3 times voltage, which gives you this. For the current flowing through various buses, since we have bus 1, bus 2, bus 3. So I1, I flowing through line 1, you can calculate it since you know the powers at the different buses. So the powers are different, but the powers at different buses here are this different, right? Okay. Uh, but the whole power in the network sums up to the power, the sum of all these powers. Okay, so using that, you can calculate the current at flowing through each of those lines or in each of those buses. Then, when you have that now, you can find the current that is fed to the relay. That is fed to the relay, which is still that, for example, for the first one, 196 times 5 on 300, right? Is times 5 on 300, which is the same thing as divided by 300 on 5. So you have the current fed through each of those relays, relay 1, relay 2, relay 3. So this gives us 3.28 da, 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 da. Since the relay characteristic was not given for the relays, we utilize the normal current that is flowing through the line and the normal current that is being fed to circuit to the relay to select now the characteristic of the relay, right? So we'll still use the relay characteristic curve of CO7. It specified that for that we have different current tap settings for CO7. Okay, we saw it up. For example, let me go back up there on this characteristic. It's very, very far. Okay, okay, CO8. Okay, CO8, CO7. So we see here, okay, it has not really been specified here. But it's usually specified as 2, 3, 4, 5, as we saw in the previous exercise. Okay, as we saw in this previous exercise, 2, 4, 5, 6, 7, 8, 12. So on. So, okay, we're here. So with respect to this, you will now select the current tap setting for each of those relays, right? So since 3.28 is closer to 4, we'll select 4 for for the first relay. Then for the second relay, we'll still select 4. 3.82 is closer to 4, right? But for third relay, we have 5.29. We'll select 6, right? Okay. So since you now have that, then during fourth, now you know that was normal condition because you use a normal condition to in order to find the characteristic of the relay if the characteristic of the relay is not given. Okay. Now, to know the faulty current that is fed to the relay, you use now the fault current on that line times 5 on 300. Hmm? So, for the fault current, as we're doing above, fault current for relay 1, 40 ampere, for relay 2, okay, yeah, for relay 1, 40 ampere. So now the plug setting or the plug multiplier setting for relay 1 will be what? That 40 ampere divided by the characteristic of the relay, which is 4, which gives us 10. So it has no unit 10, right? So 10. Now, to know the operating time, we're going to use that 10. Then now we need to look at the characteristic curve for the CO7 relay. But now, since we desire fast response on the, let's look at that characteristic curve. Okay, here's the characteristic curve. 10, we had 10. Okay, since we desire a fast response, because normally the first relay or the first relay is supposed to react, it's supposed to be react might be instantaneously. It's the second relay if the first relay is not reacting appropriately. If the first relay is not reacting, the second relay has to take over. But the second relay will be taking over now with respect to the time which the first relay was to react plus that coordination time. So the first one should react faster than the second. Okay, so if we desire the first one to react faster than the second, normally for faster operation here, we'll use this time delay setting of a half. You know we have different time delay setting here. Half, 1, 2, 3, 4. So we select that of a half. Then we come now and extrapolate. We have the current tap setting or block multiplier setting of 10. So from this 10, it cuts here on this point. So from this point now, you extrapolate, right? You extrapolate here. You'll be having about what? About 0.1 second or 0.1 something seconds. So that will be the operating time. Okay. So you come down here, equation equation okay, here now a little bit up. Okay, so for that time delay setting of a half, we have extrapolated. Here we have about 0.15 seconds. My knowledge should be 0.15 based on how we have extrapolated. Might be 0.12, yeah, 0.15. Okay, so that's the time of operation of circuit breaker 1. So if we need to know that of circuit breaker 2 is supposed to be time of circuit breaker 1 plus the time of circuit breaker 1, which is this are 0.15, which we have determined, plus what? Plus the coordination time and the error margin. You know, it was specified that let us use an error margin for circuit breaker 2. It was specified for circuit breaker 2. Okay, so I think let me go up to the question here. For circuit breaker 2, here consider an error margin of 0.3 while setting relay 2. So it's particularly for relay 2. So that's why we're adding that plus that's 0.3 seconds for the error margin. Okay, then the coordination time was as well specified, which was the operating time of each relay is 6 cycles. So those 6 cycles correspond to 0.1 second. Okay, So this is it here plus error margin, then now plus t, the operating time of the first circuit breaker, which is approximately 1 something. So that gives us 55 seconds, right? Okay, so that's it. Then if you want to determine that of circuit breaker 3 as well, you need to do the same thing. Circuit breaker 3 will be what? The coordination, the time, the time of operation of circuit breaker 2 plus the coordination time plus the error margin for circuit breaker 2, right? So you just follow the same this thing and then you apply this. All right, so you have that. Okay.